Now, we are challenging a simple torus problem. As you can see in the illustration, there are two members, AB and BC. The points A and C are joints at the wall. The members are free to rotate at these joints. You may recognize these joints are pins to fix objects at the place. Although it may be a bit of a rough expression, you may imagine a drawing pins are fixing these members. If it is not restricted at these points, but the member AB and BC hangs around the points, then these two members are joined together at point B. The lengths of the members AB and BC, which have common diameter 5 mm and Young's modulus 206 gigapascal, are both 500 mm. You may note that we are assuming these members are made from mild steel. These members are fixed at the angles of 30 degrees, which is given as theta from the horizontal in the illustration. This is the situation. These two members deforms proportional to the load when pulled downward. In this problem, we are asked to find the amount of the truss deformation. A load is acting downward at point B in the middle. In general, it is not always clear which is upward and downward, or which direction is vertical or horizontal. So, we assume that the direction of the load P is downward, and then finding the stress generated in each member to calculate the amount of deformation of the truss. These two members are symmetrically arranged, so equivalent amount of stress should be generated. The first step is to find the loads acting on the two members. Following the previous explanation, a tensile force applied to a member is positive. So, positive stress values means tension. Now, the tensile forces on the two members are defined as Q each. Some of you may wonder if the direction of the force Q should be toward the opposite direction. But you should grab the image about the situation in the following manner. First, imagine a small hole opened at the point B, and then you are pulling the hole downward at force P. Then you may intuitively understand the force applied to your finger is upward. Applying a force at point B into this direction, tensile force is generated in these members. So, considering the action-reaction relationship here, you may recognize this connection ring pulls the bar at force Q towards the direction to stretch these bars. The flow of this recognition is very important. Now, we are focusing on the bar of the left and thinking of the force Q as the force acting on the ring holding the bar. The bar is stretched toward the lower left with respect to the illustration. But this ring is pulled upwards to the right, receiving a force toward the opposite direction. The bar is stretched down to the right. In this case, this ring at point B is pulled toward the upper left. Note that the force is acting on the ring from the bars. You may imagine what happens when you put your finger into the ring here and pull it downward. When you pull the ring downward with your finger at load P, a force acts on each of the bars symmetrically in the right up direction and left up direction. We are considering the two-dimensional balance of the three forces, P and 2 of Q, in this situation. Now, these three forces are balanced and we consider the balance in the horizontal direction, the left-right direction, and the vertical direction, as in the illustration respectively. In this problem, the left-right direction is symmetrical. So, the balancing condition is almost automatically satisfied. We do not analyze the balance of the forces in the left and right directions, since both forces are Q and they are obviously balanced. So, we only need to analyze the balance of forces in the vertical direction. Then, we have the components shown in the illustration. The component in the vertical direction is q sine theta. The q sine theta is derived focusing on this triangle. So, considering the forces on the left and right side, we get twice of q sine theta. This upward force is balanced by the downward P originally acting on it. The equation describes the balance of the forces. We can derive Q with this equation. You may listen to the following explanation over and over to get a good understanding of the way of thinking. This member is assumed to be very long. Imagine that a very long member is extended by lambda and moved to this location. There is a member BC in the illustration. The member BC, which is very long, is extended by lambda and moved parallel to the original position. You should approve the image of deformation and movement first. We assume that the original member BC moves in parallel and deformed to be B'(C). You may think it should normally rotate like a compass rather than moving parallel to each other. However, in the case of this problem, where the member is very long in relation to the amount of deformation, the movement of the member can be recognized as almost in parallel. Originally, the members were connected at an angle of 30 degrees. Then now, they are slightly moved and became BC'. Considering that B'(C) is also at 30 degrees, you may notice that BC' is parallel to BC. So, now we are drawing a vertical line of BC from BC'. It is at the position of the length of elongation lambda, as shown in the illustration. You may notice that the edge of right angle triangle is equivalent to the extension of the member. The length of BC is the length of the member L. Then, the length of B'(C) is also L. Strictly speaking, B'(C) should be a gentle curve. In this case, however, we can approximate it as a straight line, considering that the angle is minute. Following the way of thinking, we can assume that the edge of the right angle triangle is equivalent to the length of elongation lambda. In fact, this idea appears in many situations regarding truss deformation. So, you should get used to this idea. A deforming member of a truss can be considered to move in parallel. Or we may consider that the point B has moved parallel after BC has been stretched by lambda. Now, we are moving on to the procedure of the next phase in this problem. We focus on this triangle. This triangle has theta as the inner angle near B, which is 30 degrees. Given that this is theta, and considering the trigonometric ratio with respect to this triangle, we can derive the relationship between lambda and delta. The procedure is as follows. Now, we have Q, which is the load applied to the member. The stress is the load Q divided by the cross-section area, recalling that the load Q is P divided by 2 sine theta. The stress is calculated by dividing it by the cross-sectional area S. Next, we consider the elongation lambda. We first calculate the strain as the stress divided by Young's modulus, and then multiplying it by the length of the member L. We have seen similar procedure before, calculating strain as stress divided by Young's modulus, and the elongation as the product of the strain and the total length of a bar or member. Now, we substitute the value as stress to get PL divided by 2SE sine theta as lambda. Then, we are using the relationship between lambda and delta, where lambda is delta sine theta. Now, we are obtaining delta from here. Considering delta is lambda over sine theta, derived from the relationship, we substitute PL divided by 2S in sine theta into lambda. Here, you may notice that the sine theta is squared. And we replace the cross-section area S by pi d squared divided by 4. Then we have now successfully expressed all the delta with the given symbols. Now, we are putting the given numbers into the symbols each for calculation. We substitute the circle ratio, the diameter, and Young's modulus. The Young's modulus is 10 to the power of 9th, so its unit is gigapascal. Substituting these values, the value of load and the length of the member, 500 millimeter, we get 494 multiplied by 10 to the power of minus 6. As we saw it before, 10 to the power of minus 6 is expressed as micro. So, the answer is 494 micrometers. In most material dynamics problems, the significant digits are 3 digits, as explained before. When the answer is calculated to be 4,944, you may just wonder how many significant digits should be used. If you set the unit as micrometer, you will get exactly 3 digits here. So, you can use the value of 3 digits as your answer. The stress acting on the member is calculated by dividing the axial force Q on the member or axial force Q by the cross-section area S. And we can get the answer by substituting given values. Now, let me emphasize a few points on this problem. First, considering that the members are long, we can assume that the torus CB before the deformation is parallel to the position after the deformation. The key point is that this allows us to consider the relationship between elongation and displacement with respect to the triangular ratio. I hope you have understood this problem. You may be still feeling uncomfortable about the first assumption that the torus member parallelly shifted and stretched without changing the initial angle. As for this, you may solve a couple of torus problems to get used to the concept.